Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss thermodynamic temperature scale, or we can say it as the absolute scale of temperature. And again, a comparison between absolute scale of temperature and perfect gas scale. So let's begin. Thermodynamic temperature scale or absolute scale of temperature. Basically, we know that different thermometers used for measuring temperature depends on property of the thermometric substance. Means which thermometric substance we used to determine the temperature of that of particular object or particular body. Hence, such thermometric scales cannot be absolute. That is the basic reason on which we can say that thermometric scale is absolute. Kelvin, the scientist Kelvin, constructed a temperature scale which is independent of the nature of working substance. Means that depend upon another thing which is does not depend on that of working substance. He used the property of Carnot's heat engine, that its efficiency is independent of the nature of working substance and it is depend upon the temperature of source and sink. He showed that this thermodynamic scale of temperature agrees with the perfect gas scale. So, what are the objectives here? In previous sections, for measuring the thermodynamic substance, the temperature of thermodynamic substance, we use the thermometric scale, but which is not absolute since it is depend upon that of working substance. But in case of Carnot's heat engine, the efficiency of Carnot's heat engine, when we studied the efficiency of reversible Carnot's heat engine, that does not depend upon the working substance. So, that is the basic principle on which, taking that Carnot's reversible heat engine, we can easily construct the absolute scale of temperature which is independent of that of working substance. Okay? So, for that reason, we take reversible Carnot's heat engine. Reversible Carnot's heat engine is considered for that particular region. Now, in case of Carnot's engine, Q1 is what? That is the amount of heat absorbed, from the source at higher temperature, let theta 1, and Q2 is the amount of heat rejected, that is the amount of heat rejected to the sink. At lower temperature? Lower temperature be theta 2, and the remaining heat which is used for doing some work. So, the efficiency will be here we take all these things. Here the efficiency will be of that reversible Carnot heat engine, eta 1 minus Q2 by Q1, means it does not depend upon that working substance, but it depend upon that heat absorbed or rejected on that of source and sink. So that efficiency depends upon the temperature. Let me take the temperature as theta 1 and theta 2. This efficiency depend upon temperatures theta 1 and theta 2, that is Q1 at temperature theta 1, Q2 at temperature theta 2. So the efficiency is a function of theta 1 and theta 2. So the efficiency is a function of theta 1 and theta 2. That is, we can write that efficiency, that is 1 minus Q2 by Q1 is a function of theta 1 and theta 2, where f is unknown, where that function is an unknown function. So we can write Q2 by Q1, Q2 by Q1 is equal to 1 minus function of theta 1 theta 2, and Q1 by Q2 will be how much, that is 1 divided by 1 minus function of theta 1 and theta 2, that can be written as the function theta 1 theta 2, where that f is unknown function, where that f is unknown function again. Let I take that is as equation number 1. Similarly, if there is another Carnot engine, similarly if we take, if there is another Carnot engine, what happened? Another Carnot engine, and which work between temperatures theta 2 and theta d, between temperatures theta 2 and theta 3, such that in that of case theta 2 is greater than theta 3. So here let we take, let Q2 amount of heat, Q2 amount of heat is absorbed by the heat engine at temperature theta 2, and Q3 is given out, that is rejected. Q2, Q3 amount is rejected at temperature what? At temperature theta 3 here. So that can be written like this: Q2 by Q3, Q2 by Q3 is again that is a function of similarly q theta 2 and theta 3, that equation number 2. Similarly again if we take another Carnot heat engine, similarly if there is third Carnot heat engine, that working between temperatures theta 1 and theta 3, temperatures theta 1 and theta 3, what happened here? Again let the q1 amount of heat is absorbed, let q1 amount of heat absorbed by that engine at temperature theta 1 and q2 amount of it is rejected, q2 amount of heat rejected at temperature theta 3. So that can be written q1 by q3 is a function of theta 1 theta 3, let equation number 3. Now multiplying these two equations, equation 2 and equation 3, now multiplying here, multiplying equation 2 and 3, what we have? q1 by q2, sorry, here is the just multiply equation 1 and 2, equation 1 and 2. So q1 by q2 into q2 by q3, q1 by q2 into q2 by q3 is equal to, that is function of theta 1 theta 2, function of theta 1 theta 2, and that multiplied with q2 by q3, that is function of theta 2 theta 3, that is function of theta 2 theta 3. So here q2 cancel out, that is q1 by q3 is equal to function of theta 1 theta 2 into function of theta 2 theta 3. Here q1 by q3 is a function of theta 1 and theta 3, so I write here that is function of theta 1 and theta 3 is equal to function of theta 1 theta 2 into function of theta 2 theta 3, that is equation number 4. Look at that equation. The LHS of that equation does not contain the term theta 2, and hence it is possible only if the function, that function can be written in that of another form. So here I write, since LHS of equation 4 does not contain theta 2, hence it is possible only if the function is in the form, that is in the another form, that is f theta 1 theta 3 is written like that, phi of theta 1 to that of phi of theta 2. And function theta 2 theta 3 like that of phi of theta 2 divided by phi of theta 3, where phi is another form. Look at this, taking that as equation number 5, that is equation number 6. So now multiplying these two equations, multiplying 5 and 6, multiplying equation 5 and 6, that will be f theta 1 theta 3 into f theta 2 theta 3 is equal to phi theta 1 divided by phi theta 2 into phi theta 2 divided by phi theta 3. Phi theta 2 cancel out, so it will be phi theta 1 divided by phi theta 3, which is a function of f theta 1 theta 3. Again, that means f theta 1 theta 3 multiplied with f theta 2 theta 3 is a function of f theta 1 theta 3. So we know f theta 1 theta 3 here at the respective points. So from equation number 5 and equation number first, look here, f theta 1 theta 2, here f theta 1 theta 2, here f theta 1 theta 2 here, since phi theta 1 theta 2. Okay, now in place of f theta 1 theta 2 I can substitute q1 by q2. So I write from equation 5 and 1, from equation 5 and 1, what we write, that means q1 by q2 is equal to phi of theta 1 divided by phi of theta 2. Since q1 is greater than q2, temperature of that of source is greater than to that of sink, therefore that phi of theta 1 is greater phi of theta 2 if theta 1 is greater that of theta 2. Hence the function phi of theta increases with the increase of theta. Hence the function phi of theta increases with increase of theta, and hence it can be used to measure, hence it can be used to measure the temperature, and let us denote that function. Let us denote phi as a function of theta by the temperature term as tau. Therefore, Q1 by Q2 denoted as tau 1 by tau 2. Again, that comparing to that of thermodynamic scale of efficiency of that of reversible heat engine. On thermodynamic scale efficiency, of reversible Carnot engine, eta is equal to 1 minus Q2 by Q1. That means 1 minus tau 1, that is tau 2 by tau 1, that is for what? Eta will be tau 2 by tau 1. That is the absolute thermodynamic scale of temperature efficiency. If tau 2 is equal to 0, a condition, if tau 2 is equal to 0 and similarly Q2 will be 0, then what happened? The efficiency will be maximum, that is 1. So, this 0 of thermodynamic scale, this 0 of thermodynamic scale, this is the 0 reading in that of thermodynamic scale. So, this 0 of thermodynamic scale is that temperature, at which Q2 will be 0, means no heat is rejected, to sink, and all heat removed from the source is converted into useful work. So, this is thermodynamic scale of temperature or absolute scale of temperature, This is a thermodynamic temperature scale or absolute scale of temperature that finally take it. Now, we derive a comparison between absolute scale and perfect gas scale. So, a comparison of absolute scale and perfect gas scale. We know that on that of thermodynamic scale, we know in thermodynamic scale the efficiency eta will be 1 minus tau 2 by tau 1. If tau 2 0, then efficiency will be maximum. This is what? This is in thermodynamic scale. But on gas scale, gas scale efficiency eta will be 1 minus T2 by T1. Again here if T2 0, then eta is 1 maximum. Look at these two cases. Here eta is maximum 1, here eta, that the efficiency is maximum. So we can equate these two. Hence 0 of thermodynamic scale is the same as 0 of perfect gas scale. This is the perfect gas scale. So that is equation 1, that is equation 2. So from equation 1 and 2, tau 2 by tau 1 is equal to T2 by T1, then 1 minus tau 2 by tau 1 is equal to 1 minus T2 by T1, or that is tau 1 minus tau 2 divided by tau 1 is equal to T1 minus T2 divided by T1. That is equation number 3. Look that equation. If the heat engine works between melting point of ice and boiling point of water, what happened? If the heat engine works between melting point of ice and boiling point of water, then what happened? Then T1 minus T2 will be 100 here. T1 minus T2 will be 100 here, and tau 1 minus tau 2 will be 100. So equation 3 becomes, in place of T1 minus T2 and tau 1 minus tau 2, we put the values. So 100 divided by tau 1 is same as 100 divided by T1. Therefore tau 1 is equal to T1. This is a first relation, tau 1 same as T1, means that can be written like here. Hence boiling temperature of water is same on both perfect gas scale and thermodynamic scale. So tau 1 is equal to T1. Again for that of melting point case, that will be 0. Tau 1 minus tau 2 will be 0. Tau 1 minus T1 is same as that of T2 is same as that of tau 2. Again from that of equation here is that of equation number. From that equation tau 2 is same as T2, since tau 1 is equal to T1. So tau 2 by tau 1 is equal to T2 by T1, or tau 2 is same as T2. Hence we can write, hence temperature of melting ice is same on both perfect gas scale and thermodynamic scale. Look here, tau 1 is equal to T1, that means boiling temperature of water is same for perfect gas scale and thermodynamic scale. Here tau 2 is same as T2, that the temperature of melting ice is same as that of both perfect gas scale and thermodynamic scale. From these two equations, it is clear that both perfect gas scale and thermodynamic scale of temperature are identical. Hence, overall we can write, hence both perfect gas scale and thermodynamic scale of temperature are identical. Okay. So here we studied about comparison of absolute scale and perfect gas scale, and finally we take perfect gas scale and thermodynamic scale of temperature are identical. So with the help of this video lecture, we understand what is thermodynamic temperature of scale, or we can say it as the absolute scale of temperature. We are taking the reversible Carnot's heat engine concept and mathematical procedures, like take the function, taking the study of these equations, and finally derive the relation for that of absolute temperature of scale, absolute scale of temperature, or absolute scale of temperature, or we can say it as the thermodynamic temperature scale, and the comparison of absolute scale and perfect gas scale. Finally we observe that these two scales are identical. So with this useful and informative notes, let me wind up this session. Thank you.